So, we had seen that Galilean transformation preserves acceleration. If you have two inertial frames and you are looking at a particle from this frame and that frame, and you find that acceleration of the particle in the first frame is some a, then the same acceleration will be from the other frame also. So, that is the Galilean transformation, this remains same. Then forces which are generated because of interaction of particles, normally they are dependent on the separation between the particles like gravitational force or Coulomb force, and distances for low velocities at least, they do not change from one frame to other frame, and therefore, the forces can also be taken as same in one frame and in other frame. In that case, and mass is of course the same here and there, and therefore, if you have this equation F equal to ma, Newton's second law, and if this is valid, in S, if it is valid in S, F is equal to ma, the same quantities when I transform according to Galilean transformation and write from S prime, then I find that okay, there also it is F remains F, M remains M, A remains A. You have the same form. That is principle of relativity. The laws of physics are of same form in all inertial frames, and therefore, any experiment which is controlled by this equation, if I do in S and I do in S prime, I get the same results. So, that is very nice. Galilean transformation, Newton's law, principle of relativity, everything is very nice. But then when it comes to speed of light, which is same in all inertial frames of reference, Galilean transformations do not work, because in Galilean transformation we had seen that ux prime is equal to ux minus v and uy prime is equal to uy and uz prime is equal to uz. So, if I calculate speed ux square plus uy square plus uz square root, that is the speed. So, speed in S frame and speed in S prime frame can never be equal, but in case of light they have to be equal. So, that means the Galilean transformation is okay for Newton's law, but Galilean transformation is not okay for optics laws or Maxwell's laws or electricity, magnetism, field, electric field, magnetic field laws. So, what we say is Newton's laws is invariant under Galilean transformation, but Maxwell's laws, which describes the behavior of electric field, magnetic field, electromagnetic wave, Maxwell's laws are not invariant under Galilean transformation. If that be the case, then if you design an experiment based on these Maxwell's laws, electricity, magnetism, optics experiment, that will give different results in different inertial frames, which is again contradictory to our first postulate of principle of relativity. So, if Maxwell's laws are actually the laws of physics describing electric field and magnetic field, Galilean transformation has to be modified. That is not the way nature transforms from one frame to other frame. And if that Galilean transformations are to be modified, then that modified transformations equations, whether they satisfy keep this Newton's law invariant or not, that will be another question. But that question we will discuss later. First thing is that principle of relativity, if I believe, if I put it as a postulate, it has to be believed, and constancy of speed of light has to be believed, then the Galilean transformations have to be modified. Okay. So, that modification is done, and the new transformation equations which we come up, that is called Lorentz transformation, which ensures that speed of light is same in all inertial frames, and under those Lorentz transformations Maxwell's equations are invariant. So, what are those Lorentz transformations and how to get it, how to get those transformation equations, that is the thing we will be discussing. So, I will be using one is principle of relativity, that is one. Then the second is constancy of speed of light. My Lorentz transformation must conform to this, speed of light, of course in vacuum, right, that should be understood. Then I will use two more things. One is homogeneity. Homogeneity of space, that will be using, and time. I will just explain what it is, and isotropy. So, these two we have discussed several times. Homogeneity of space. Homogeneity of space is space by itself is identical everywhere, that is called homogeneity of space. So, if you perform an experiment here or perform an experiment somewhere else, same experiment, your result must be the same. Laws of physics here and laws of physics there are same. In all parts of space, laws of physics are same. So, it is a big statement, but okay, we believe that yes, space is homogeneous. In space there is no problem. When you put material in the space, then of course you are changing the environments. So, if near the star or near the earth or near this table or near this blackboard, that is a different story, but space by itself is same everywhere. If you construct the same kind of material somewhere else, that also will behave in identical way, that behavior you see here. So, that is homogeneity of space. Then you have a homogeneity of time. Homogeneity of time. Time is also homogeneous. That means the laws of physics now and the laws of physics million years ago and the laws of physics yet to come million years ahead of time, it is always the same. Time is homogeneous. The laws of physics do not depend on in which year you are working or in which month you are working, at what hour you are working, it does not depend on that. Of course, we are discovering the laws of physics, and therefore, it is possible that in 19th century we had certain different laws of physics, and in 21st century we are having certain different laws of physics. Laws of physics have not changed. our knowledge of laws of physics has changed. So, that is the homogeneity of time, time is homogeneous. And then you have isotropy of space, all directions in space are similar, are identical, are equivalent, all direction in space. When I put some material, then of course I can give the directions, special directions. If I have two materials, in hand, yes, there is a special direction which is connecting these two, but space by itself, the properties of space by itself, is same in all directions, that is known as isotropy of space. So, these are the things that we will be using to derive this Lorentz transformation. So, start with two frames S and S prime, and as I said in the previous lecture, whenever I use S and S prime, this nomenclature, the meaning will always be same. You have two frames S and S prime, and the x axis and x prime axis are identical on the same line, x prime here, x here, y prime are parallel, z and z prime are parallel, the origin here, and this S prime will move with respect to S with a velocity v in the positive x direction. So, that will be our definition of S prime. S prime will move in the positive x direction with respect to S. So, it is not that S is at rest and S prime is moving, there is no absolute rest. You can very well say that S prime is at rest, S is moving, but then S is moving in the negative x direction. So, this will be our the two frames S and S prime. And what we are looking at is some event somewhere at this point, at a certain, some event has taken place, a glass has been broken there, some event has taken place. So, from S we ask where was that event. So, the answer to that where is that it occurred at this position, that event occurred at this position. At what time? The answer is at time t. And same question to S prime, where did the event occur? And the answer is x prime, y prime, z prime. When did it occur? The answer is t prime. So, we have to connect these things and these things, that is transformation equations. Now, first thing is, if I try to write this expression of x prime in terms of x, y, z, t, I can write it as some constant times x, some constant times y, some constant times z, and some constant times t. And similarly for y prime, for z prime, and for t prime. So, the first thing that I have done here, I have already used something of these, I have already used something here. I have used homogeneity of space, I have written, and time also. I have written first power in x, first power in y, first power in z, first power in t. That is because space is homogeneous. If I do an experiment here, if I do an experiment there, it does not matter. So, if I have something else, say x square or x cube or something else, in that case you can very well see that it depends now where actually where is what is a value of x1, what is the value of x2, and like that. If that value is somewhere else, if the same thing is happening somewhere else and x becomes, let us say, x plus alpha and y becomes y plus beta and squares are involved, then you will see that what is happening here and what is happening there is different. So, homogeneity of space is violated. So, first power. So, that is one thing. Second thing is, although we can start with these sets of 4 these kind of equations, and the book by Robert Resnick on special theory of relativity actually does that, but I will cut short the mathematics. The final result I know and I can justify, and that is that in this expression, since the motion is in x direction, there is no motion in y direction. So, this y part and z part, that does not appear in this expression of x prime. So, it is not an assumption, we can justify, we can derive, but I will cut short that mathematics, I will just write that as, let us say, some constant times x and some constant times t. Time is there, time is, we are keeping time, and we will see that yes, it will be there. The space part transformation also involves time, first order, of course, time is also homogeneous, but this is there. So, we just keep it. Y prime is y, in y direction there is no motion between s and s prime, and y coordinate does not change. Once again, it is just not an assumption, we can derive it, we can justify it, but I am not going in that much of mathematics. Take this. So, this will be there, and then we have t prime. So, t prime will again be dependent on x and t. So, this will be, let us write it as c, I do not want to write, c is the speed of light. So, let us write d and x and plus f and t. So, we start with these equations, these two are already we have taken it granted, and for these two we are writing these, we have to find a, we have to find b, we have to find d, and we have to find f. And for that we will be considering certain special kind of events, and then we will use this to find the location and time of that event here and there, and use this principle of relativity and constancy of speed of light and isotropy of space to derive a, b, c, d, a, b, d, f for those very specific events that I will be choosing. But remember, these are transformation equations, these are general, these are valid for all events, and therefore, even if I pick up some special event and get the value of a, b, c, d or a, b, d, f, those same values will be there for all events. So, although I will be using very special kind of events, but the results that I am going to get will be applicable to all kinds of events. So, let us now start with that. So, the first event I consider is an event which has taken place at time t and position x equal to v t. So, I am considering an event, and the event is as seen from S, it occurs at x coordinate vt, y coordinate 0, z coordinate 0 and time t. So, I am just looking from S, and remember, when origins cross O prime and O cross each other, that is our t equal to 0 and also t prime equal to 0. So, with that t equal to 0, when origin O prime was crossing O, that was t equal to 0 here, and then an event occurred at time t, where vt comma 0 comma 0, that means from here vt distance away on the x axis, and that is the position of O prime, because this S prime is moving with velocity v as seen from S. So, as seen from S, this origin O prime is also moving with velocity v, and hence the origin O prime will move v into t distance in time t. So, this event has actually occurred at the origin O prime. So, if it occurs at Vt 0 0 at time t, that means this occurred at O prime, and therefore from S prime frame, what is the coordinate of that event? Where did that event occur? That event occurred at x prime equal to 0, y prime equal to 0 and z prime equal to 0 at the origin O prime itself. So, this occurs at O. So, from S prime this occurs at x prime equal to 0, y prime is equal to 0, z prime equal to 0. This was x, this was x, x is equal to Vt, y was 0 and z was 0. Now use this equation, x prime should be equal to ax plus bt. X prime is 0, x is Vt and t is t. So, use this equation, this particular equation. What do I get? 0 equal to x prime is 0. So, 0 is equal to a into x, x is Vt, x is Vt plus b into t. Take t common, av plus b into t. And this equation is correct for all t. You can take any event which are related by this equation. Take t equal to 10 seconds and then calculate Vt and consider this particular event. Take t equal to 20 seconds and then construct this Vt, 20 seconds into velocity, x is equal to that, and then here 20 seconds, you write an equation, 30 seconds, 5 seconds, 0.5 seconds, whatever, minus 2 seconds, whatever. So, this equation is valid for all varieties of t. Whatever value of t you put here, this equation will be valid, and that means that this is 0, av plus b is 0. av plus b is 0 or b is equal to minus av. So, let me put it here, let me put it here. What do I get? X prime is equal to, x prime is equal to ax plus bt and b is minus av. So, minus av into t, and therefore, x prime is equal to ax minus vt. So, x and t will come in this combination, some constant into x minus vt, that will be x prime. Now, I take another events, 3 events in fact I will be taking, one phenomena but 3 events, and from there I will get more equations to get the actual value of a and this d and f also. So, now I will take 3 more events. We will take one phenomena and or one actually one event, and that will result in 3 events. And what is that event? Let me tell. That event is that when the origins were crossing each other, when the origins were crossing each other, that is t equal to 0, t prime equal to 0. At that time, a pulse is generated, an electromagnetic wave is radiated, short pulse, but which spreads in all directions. So, and a light pulse, let us call it light pulse. A light pulse is radiated from the common origin. So when this S prime is moving with respect to S, it comes from left, and then when just crosses O prime crosses O, at that time some electromagnetic radiation is emitted, and that spreads in all directions. So it is radiated from the common origin and spreads in all directions. After that, we will take some events. This electromagnetic radiation reaches here, or it reaches here, or it reaches there. So that way we will construct 3 events, and from these 3 events again we will get equations like this, and from there we will try to find what is A, what is D, and what is F, and finally the Lorentz transformation equations.